Welcome to Database History. Now, in this series, we usually dig into how databases have evolved over time. But today, we're exploring what happens when they don't. We're diving into the dark side. What happens when ancient, decades-old database logic crashes headfirst into our modern lives, creating a trap that can snare, well, pretty much any one of us. Ugh, you know this feeling. We've all been there, right? You're at the DMV, just trying to renew your car registration. Everything seems to be going smoothly, and then the clerk hits you with that dreaded line. You ask why. They just kind of shrug. Says here, toll violation. But you paid that. Today, we're going to peel back the layers on that exact moment of frustration and show you what's really going on behind that screen. This is the story of the 7-day latency trap.
All right, let's get into it. Here's our game plan. First, we'll look at why the computer says no. Then, we'll take a trip back to what I call the Iron Age of data to really understand the kinds of systems we're up against. From there, we'll expose the 7-day latency trap itself, see how it led to an absolute nightmare in our dead battery case file, and then, finally, we'll pinpoint the exact fatal flaw in the code.
Okay, Section 1, the Iron Age of data. See, to get to the bottom of today's problem, we have to jump in a time machine. The supercritical systems that run things like the DMV, well, they weren't built yesterday. They weren't even built in the cloud era. They were forged back in the 1970s and 80s, an era of giant mainframe computers and, this is key, a totally different set of rules for how data moves around. Back then, in the mainframe era, computing wasn't instant. It wasn't real time. Everything ran in what's called batch jobs. Think of it like this. If you paid a fine on a Monday, the system didn't just instantly update. Nope. It collected all of the day's transactions, and the day after, and the day after that, and then processed them all together in one massive chunk, probably late on a Sunday night. Now, for the time, this was super efficient, but that built-in delay, that's the first crack in the foundation of our entire problem. And this timeline really shows you the collision we're talking about. On one side, you've got these systems from the 70s and 80s built for batch processing. On the other side, you've got us, here in the modern world, expecting everything to be instant, real-time through APIs. When you try to force these two completely different eras to talk to each other without a total overhaul, you get what's called a modernization crisis. And that is exactly where our story begins. Which brings us right to Section 2, the 7-day latency trap. This is the name for that administrative limbo, that black hole created by the modernization crisis. You know, in a perfect world, the toll authority and the DMV would have a live, real-time connection. You pay a fine and boom, the block on your registration vanishes instantly. But that's just not how these old systems work. Instead, they rely on a clunky old process built around something called a Scofflaw List. The process is, and I'm not exaggerating here, shockingly manual. So, once a week, the toll authority's database runs one of those batch jobs to spit out a list of every single person who owes them money. That list gets exported to a giant text file. Then, that file gets sent over to the DMV. The DMV system then has to import that entire file and automatically block every account on it. It is literally the digital equivalent of sending a critical, time-sensitive memo by snail mail. Now, this slow weekly process doesn't just create annoying delays. It creates a classic, and I mean critical, software flaw. It's called a race condition. This is a situation where the whole system's behavior depends on the random timing of separate events. In our case, the two events are you paying your fine and the system sending its weekly file. And they are in a race, and you have no idea who's going to win. So here's how the trap springs on you. Let's say you get a notice, and you pay your fine on a Monday morning. Great. In the toll authority's modern database, your account is cleared instantly. You owe $0. But the DMV's ancient system is still working off of last week's file, the file they got last Friday, which lists you as a violator. So for up to 7 days, you literally exist in two states at once. You're innocent in one system, but you're guilty in another. You are trapped in administrative limbo, all because of bad architecture. Now look, this isn't just some theoretical inconvenience. This has real, devastating consequences. And that brings us to Section 3, our case file, dead battery. We're going to look at a real incident out of Rhode Island where this exact architectural flaw turned a simple hardware failure into a legal nightmare for thousands and thousands of innocent drivers.
It just sounds absurd when you say it out loud, doesn't it? I mean, how on earth does a dead battery in your little E-ZPass transponder somehow result in a $50 fine and a block on your car registration? Let's break down exactly how the system's broken logic made this happen.
So the whole problem starts with a really simple piece of hardware. Your E-ZPass has a battery in it, and it lasts for about a decade. But here's the catch, and it is a big one. There's no warning light, no little beep, it just dies. And when that happens, the toll booth can't read the signal, so its backup system kicks in. A camera snaps a picture of your license plate. Simple enough, right? Now, a human, a person with common sense, would look at this situation, check the license plate, see it's linked to a valid E-ZPass account that has plenty of money in it, and think, the transponder must be dead. They just deduct the toll and maybe send a notice. But the database logic, it wasn't designed to be smart, it was designed to be ruthless. So for our final section, let's go find the smoking gun. We are going to look at the exact flaw in the code, the specific piece of database logic that turned thousands of paying customers into violators overnight, all because of a dead battery.
And here it is. The logic is brutally, terribly simple. If the transponder signal is missing, then slap them with a $50 violation fee and flag the account to block their registration. Period. It makes a fatal assumption. It assumes that a missing signal automatically means a violation. It never, ever stops to ask the most important question. Wait a minute, is this license plate linked to a valid funded account?
And what's so maddening is that the fix would have been just so simple. The alternative logic is just plain common sense. Before you assume it's a violation, the system should first check if the license plate from the camera picture is linked to an active account with money in it. That one simple check would have prevented this entire fiasco. So the next time you hear the computer says no, I want you to remember this chain reaction. It starts with bad architecture, like those weekly batch jobs, which creates latency. That latency creates race conditions, and that opens the door for ruthless logic, which fails to account for simple things like hardware failures, to punish innocent people. The huge lesson here for anyone who builds or manages systems is this. You have to design for the edge cases. You have to plan for failure. And this really leaves us with one final thought. This isn't just about toll roads or the DMV. It's about how we design technology to interact with actual human beings. So I'll leave you with this question to think about. What are the hidden dead batteries, the simple, predictable failures waiting to happen in the systems that you build or that you rely on every single day? Thanks for joining me on Database History.